Hi students. I'm going to try to talk through the LaGrange air-bound formula a little bit one more time and see if that helps you. It's not, I feel like the textbook problems are not great, so that's part of the problem, but we're just going to talk through this and maybe you'll see why this is hard. So first of all, the LaGrange air-bound is going to tell you a maximum bound on how bad your estimate is. So it's not going to be perfect, and it's not about finding the amount of error. That would be absolute error. If you were able to calculate absolute error, that would tell you what the error is. But the LaGrange air-bound is saying, I know, without doing that calculation, I know that my error is no bigger than this. Okay? So anytime when we use LaGrange air-bound, we're going to be going for estimating high. Okay. So I tried to write my variables in different colors. If you're colorblind, I apologize. But n is going to be the degree of the polynomial that we're using as an estimate. Okay, so the error, if I use like a third degree polynomial, n would be 3. Okay. X is going to be the coordinate at which we're going to evaluate our function. So if we want to calculate the LaGrange air-bound, we're going to need to have an x value because we'll plug that into this function and then we'll plug it in here. So notice how the air-bound formula looks a lot like just the next term in the series. And it almost is just the next term in the series. It's still shifted, so if it's not centered at 0, it's going to be shifted. And so that's what the x minus a is. That's for if it's not centered at 0. And you're increasing the exponent by 1. You're increasing the factorial by 1. You're increasing the derivative by 1. But again, they all match, just like they do when you have a term in a Taylor series. And the only thing different is instead of evaluating the derivative at a, which is what we do when it's the next term in the series, we're going to evaluate the derivative at z, and z has to be some number between x and a. And we're choosing a z that will make the derivative as big as possible. The kind of things to think about as you're choosing z is, first of all, it doesn't really matter what z is. We don't really care what z is. We care what the derivative evaluated at z is. So sometimes we never really know what z is. The other things to think about are if your derivative is a sine or cosine function, and you know how sine and cosine cycles through, and you might not know exactly where you are in that cycle. It doesn't matter because the output for sine and cosine is never going to be any bigger than 1. So a lot of times, if we're doing the LaGrange air-bound and we have to estimate this derivative, this one more derivative, we say, you know what, if it's sine or cosine, we're just going to call that 1 because we're dividing by n plus 1 factorial. We have an n plus 1 to the power. So really the magnitude of this, if it's between -1 and 1, we're going to just make it as big as possible and call it 1. It's not perfect, but the LaGrange air-bound is not about being perfect. It's about overestimating and saying, I have 100% certainty that my estimate using a polynomial is at least this good. So the LaGrange air-bound should actually be an overestimate of what your error is. It's going to be bigger than your absolute error. Okay? And so we want to maximize this thing. As calculus students, we're really good at maximizing stuff. Okay? We know that if our function is increasing, then we want to make z as big as possible because our function is increasing. If our function is decreasing, if this derivative is decreasing, we'd want to make z as little as possible because that's decreasing. If our function is an exponential function, we know that's an increasing function. So it does require some function knowledge in order to choose this derivative to be as big as possible. But that's what you're going for. You're trying to maximize this derivative. Often it's by making z either x or a. often your z will be one of the endpoints. Okay. The other trick is that if you're dealing with sine or cosine, we just say, I don't know what z is, and I just am going to estimate this as 1, because the derivative of sine and cosine is just sine and cosine. The biggest output for sine and cosine, whatever z is going to be 1. So we say, all right, we're going to just estimate that as 1. So I had to grab into my toolbox and grab a whole bunch of colors, and the reason I had to grab so many colors is because there are lots of things going on in this formula. The one thing that should be comforting is that when you memorize your Taylor series function, this is just the next term. All this n plus 1 factorial and n plus 1 is the exponent and n plus 1 is the derivative just means, okay, we're going to look at the next term. We're not exactly going to look at the next term because we're just not evaluating this at a necessarily. We're going to evaluate it at the point that makes that derivative as big as possible. Okay, so that's my summary of Lagrange error bound. It's tough, and you can do it. So that's our plan. I put some more practice on there so that you can practice this a little bit. I was going to walk through the first problem and make a video of that as well, so I'll work on that too. So I would strongly recommend that you try that worksheet. It's not really laid out as a worksheet anyway, so you can pull it up on your screen and then write on a separate sheet of paper. Okay. Thanks, you guys. Good luck.